Hello, everybody. So we are now discussing one new point regarding the combustion or mass balance on combustion reactions, and this video will be discussing the difference between the two terms that we see here, which are the dry bases and the wet bases of air. And these are very common terms that we use to describe the composition of air or the composition of gases in the flue or in the flue gases of a combustion unit or a combustion chamber, and we know that the combustion products will include carbon dioxide, carbon monoxide, nitrogen, oxygen, some of the fuel, and water vapor. And I think it's clear that when we say dry or wet bases, it's something that is related to water vapor, not any other gas in the mixture. So when we say the composition on a dry basis, it means that the composition of the mixture excluding water vapor. So we take all the compositions or all the number of moles, and we exclude that of water vapor. Of course, we do not do this in reality, but we do this for calculations. We just include all the gases except water vapor. For the wet bases, we are doing the same, but we are calculating the compositions including water vapor. So this is the only difference between the compositions on the wet bases or dry bases. But before so this is all what I want to say regarding the definition, and this is everything. There is nothing special about the calculations other than including or excluding water vapor. It's as simple as this. But the point I want to discuss here is why specifically water vapor is the gas that or the component that we are considering in the two cases, whether to include it or exclude it from the calculations. Why don't we, for example, calculate the composition of the mixture excluding nitrogen, and to call this the nitrogen free bases composition, for example. And we can say that nitrogen is not part of the reaction, it's just an inert gas that enters the reaction with oxygen, so it's not something that we want inside, so we can just exclude it. And this is a very important point, why we consider water vapor and not any other gas. And the answer is very simple, and it's very, very reasonable also. If you look at all the gases, you would see that these gases that we mentioned, the carbon dioxide, the carbon monoxide, water vapor, and all these things are gases. And the water is vapor. And there is a big difference between a vapor and a gas. A vapor is, both are gas phase components, but the vapor is condensable, meaning that you can convert this component from a gas phase component into a liquid phase component, from a vapor into liquid. And this is by condensation. So water can condense under ambient conditions. So this is something that makes water different from all the rest of the gases. We cannot do this for oxygen, for nitrogen, for carbon dioxide, for carbon monoxide. We cannot condense these gases. Water can, and I think this is something that you have all seen before, that water can condense easily under any conditions. This is something that you can do yourself if you see any humid day. If you look at any surface, the windshields of the cars, the plant leaves, you can see water drops on these surfaces, and this is simply because water is condensing. So when water condenses, it means that its amount in the gas phase is decreasing. And also it can increase. If you have, let's say, a rainy day, then the rain will increase the humidity or the water vapor concentration in air. If there is a hot day and there is a water surface close to you, a river or a sea, you can see that the water vapor in air increases. The concentration of water vapor increases. So the water vapor is the component that is variable regarding the number of moles in the gas phase. Of course, other gases can condense, but these gases will condense at very, very low temperatures or at very high pressures, and we will discuss this in energy balance in some details. But if you for example, think of liquid nitrogen or dry ice, which is solid carbon dioxide, they are solids and liquids at very, very low temperatures. This means that it has to go down to negative 100 and something to reach this temperature, and that's why you cannot condense them under ambient conditions. And this is something that you can see for the very, very cold countries. If there is a snowy country that the temperature goes below like 20 or 30 degrees Celsius, a negative 20 or negative 30 degrees Celsius, still oxygen and nitrogen are gases. So they're not gases that can easily condense. So this is why we care more about water vapor here. So anyways, I just wanted to make this point clear, and then the rest is just simple calculations. It's just you include it or don't include it. So for this mixture that we have here, it contains oxygen, nitrogen, carbon dioxide, water vapor, and methane, and we have all the number of moles as you see here, and we want to calculate the composition on wet and dry bases. So with dry bases means that we are including everything, excluding, and we are not including water vapor. So the composition, which is the mole fraction, is the number of moles over the total number of moles. So it's going to be the sum of all these number of moles except the 35 degrees. So this is the mole fractions. You divide each one of these numbers by the total number of moles. For the weight bases, it's the same, but we include water vapor. Of course, there is no mole fraction of water vapor here because we exclude water vapor. So it has no meaning that you calculate the water vapor mole fraction on dry bases. So it's a contradicting sentence. So on wet bases we can do the same, and we can include water as the number of moles of water, and then we can calculate the mole fraction as number of moles divided by the total number of moles for all of them. So it's as simple as this. So it's nothing that we need to spend time discussing. There is another example here. It's a nice one, and in this example it's in two parts. The first part is very simple. We have a mixture of nitrogen, carbon dioxide, oxygen, and the balance is water. And we know the mole fraction. So water is 15%, and we need to calculate the composition on dry bases. So as we said, dry bases excluding water vapor. So we can assume a basis. And for this basis, let's say 100 moles, so we know the number of moles of each one of them, and it's exactly the previous problem. We divide or we calculate the total number of moles excluding water vapor, which will be 85 moles, and then we divide each one by the 85. So now we get the compositions on dry bases. So it's very simple. The next part is the interesting one. So it says that the water vapor content in the gas mixture increases up to 25 mole percent. And we need to find the composition of the gas mixture on weight basis. So this is an interesting thing. So we know now the compositions on dry bases, and we know on the 100 mole basis we have all these number of moles. So if the mole fraction of water, which is originally 15%, increases to 25, it means that the number of moles of water vapor increased, and instead of being 15%, it became 25%. And we know from long time ago, the beginning of this course, is that the total or the summation of the mole fractions must be 1. So if this became 25%, it means that the rest of the components are 75%. So their mole fraction decreased, and instead of being 85%, became 75%. So one thing we can do is so we expect that each one of these numbers would decrease. Each one of these numbers decreased because it was originally this 0.1 was 10 over 100, and now this is not 15 anymore. It's a bit bigger number. So the total number of moles became higher. So it's 10 over a bigger number. So its value decreased. So what we can do is simply this is what we originally had in the beginning, and now based on the 100 moles that we assumed in the previous part, we can say that the number of moles of all of them is the same. And this is what I was saying, that the number of moles of the rest of the gases is going to be constant. So they're going to be the same. The only difference is that their mole fraction will decrease because the number of moles of water increased, but I don't know the new number of moles of water. So what we can do is we can calculate the total number of moles as a function of the new number of moles of water. So it's now 85 plus the new number of moles of water, and now we can use the definition of the mole fraction, which is this 25%. So the 25% is the number of moles of water divided by the total number of moles, which is 85 plus the new number of moles of water, which would be 0.25. So this is a very easy equation to solve. So now we can calculate the number of moles of water to be 28.33. And from this we now know the total number of moles, and we can divide each one of them by the total number of moles, and we can get the mole fraction of the component. There are other methods that you can use, but they're all going to do the same thing at the end. So that's it. So this is all what I want to discuss in this video. We have only one more point to discuss before we put everything together and start to look at some combustion problems. So I'll see you next time, inshallah.